Hi, year 12. So I've gone a wee bit rogue here and I've only put space questions into your retrieval roulette, okay? So pause and answer those for me, please, and thank you. Oh, remember in that question 7, that should really be 3 times 10 to the power of 8, not 3 times 108. Okay, so here are your answers for marking, correcting those. Get that done, thank you very much, and then start to play again whenever you're ready. Okay, so if you open up your notes back where we finished off last day, so we were doing these questions that started on page 236 about that Faraday's ring experiment. So this diagram here, if the magnet is stationary above the coil, the reading on the center 0 ammeter is 0. When the north pole of the magnet moves into the coil, the needle moves to the right. When the magnet is stationary, the needle on the ammeter returns to 0. Right, so part 1, what name is given to this effect? Electromagnetic induction. And then part 2, explain these observations. All I have put here is that the magnetic field or wire moving relative to each other induces a current in the wire. So either the magnetic field is moving or the wire is moving. But as long as they're moving relative to each other, you're going to get a current induced in the wire. So be marking and correcting these. It doesn't have to be worded exactly the same as mine, but you know what I mean, just as long as the general gist is the same, or if you want to add in anything of mine, obviously work away. Right, and for part B, describe what would be observed when the magnet is pulled up out of the coil. Well, then the needle's going to deflect the other way, and it had told us here that whenever it was going down in, it moved to the right, so whenever it's coming up, it's going to go to the left. See, what energy provides the source for the electrical energy in the coil? I was like, oh, but then it was like the magnetic energy, the magnetic field energy, and the kinetic energy of the movement as well. Okay, 10. So we've got Faraday's ring experiment set up here. And then part A asks us to explain why a current flows in the secondary coil when the switch is closed. So generally, whenever I'm writing these answers, I'm generally writing them so that it's easy for me to check your answers for a quick comparison, but I wasn't really able to do it nice and short for these. So when a switch is closed in the primary circuit, this one, current flows and a magnetic field is produced. So whenever that switch is closed, magnetic current starts to flow, so it goes from 0 to being a set value of current, and the magnetic field is going to grow out of there. The magnetic field lines cut across the secondary coil, so they're growing out this way, and a current is induced in the secondary coil. Okay. Now over the page then, explain why a current flows in the secondary coil when the switch is then opened. So whenever the switch is opened again, then the current's going to stop. So I think that's what I've said here. When the switch is opened, the current in the primary coil reduces down to 0. So your magnetic field is going to shrink back again. So what way did I say that? So the magnetic field strength decreases and the field lines cut across the secondary coil in the opposite direction. And then I put in there like as it shrinks back. So if I go back to this diagram, whenever the switch was closed, the magnetic field grew out, cut across here and induced a current. Whenever the switch is opened again, so it's going to stop the current, then the magnetic field is going to shrink back, cut across this in the opposite direction, so it's going to induce another current in there. See, what way is the current in the secondary coil different? It's just opposite directions. Maybe opposite would have been better there rather than different. D, how could the apparatus be changed to produce an AC current in the secondary coil? Well, if we had an AC current in the primary coil, then, if I go back here, here's our primary coil. If this was alternating current and it was always changing directions, then you're going to end up with an alternating current in there because your magnetic field line will constantly be cutting across. Now, 11. So this is really going back to this here stuff, I think it was, wasn't it? So state the relationship between the size of the induced current and the speed of the magnet. Yeah, so the faster the magnet is, the higher your current is going to be. 12. State the relationship between the direction of the induced current and the direction of the magnet's motion. I didn't get too specific here. You could have really talked there about, where is it, page 228, Lenz's law. Do you remember we looked at how you could figure out that direction? But I just said here that the induced current is going to change direction as the magnet's motion changes direction. So as the magnet changes direction, the current is going to change direction. And then state how alternating current can be induced using a coil and a magnet. If you just keep moving the magnet in of the coil and out of the coil over and over again, then you're going to end up with an alternating current, because with that change in direction of the magnet, the current's going to change direction. Hopefully that has helped people who were stuck on those questions, but if there's anything that you're not sure about, remember, do keep on at me, keep asking me. Okay, now that stuff we looked at last day, the Faraday's ring experiment, is the basis for transformers. So transformers are used either really to step up a current or step down a current, or I should say step up voltage or step down voltage. So that's what we're going to look at today, right? We need to fill in some definitions here, so I'm going to write them in and then I'll be back to go through it with you. So we've got here, I'm going to hide that. Oh, sorry, I'm going to hide that just so you are listening to me and not frantically writing that down. So we've got, it's very, 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 very similar to what we were talking about last day. We've got an iron core, we've got a primary circuit and a secondary circuit, or a primary coil and a secondary coil. So in a transformer, this primary coil would be connected to an alternating current supply, and then your secondary coil is like your output supply. So this one here, see the way we've got like a wee small number of coils here and then loads of coils here? This would be a step up transformer. So this would be one where you could use a small power supply to get a really, really high voltage out, right? Then this one here, we've got our primary coil and our secondary coil, and this one, see the way on the primary we've got really, really high number of turns of the coil, and then this one we've got low, so this one will be called a step down voltage because the secondary is going to be lower than the primary. And then that wee bit down at the bottom is just like how it would be drawn in a circuit. I don't think we ever really draw them in circuits. So definitions: the primary coil is where the input voltage is, and whenever we're using our equation to do calculations here, V subscript P is how we write that. So the input voltage is connected to that coil. Secondary coil is going to provide your output voltage, and we call it VS, so voltage secondary to your external circuit. Sorry, did I give you time? Pause, get those written in for me, please. And then the laminated iron core. Laminated is just there to show you that like the current can't travel along here. It links the two coils magnetically, so write that down for me as well, please. So I'm on 240 now, in case you hadn't noticed. I'm sorry, I'm going to read through this, but sort of like interject as we go. I know that's not the most exciting. So, how do transformers work? When current in a coil is switched on or switched off or changed, a voltage will be induced in a neighbouring coil. This effect is called mutual induction. So, in the above diagram, let me see if I can get one to have on the screen at the same time. Okay, I'm very technologically minded. I've got my old version of the notes there wrecked. Okay, so two coils, primary and secondary, they're not connected in any way. So switching on the current in the primary coil, this one, so remember these are connected to like a power supply. So if we turn on the current here, that's going to set up a magnetic field, and as the current is like turned on, the magnetic field is going to grow, cut across the secondary coil. Right, so that's all that's saying there. So switched on the current in the primary coil sets up a magnetic field, and as the field lines grow outwards from the primary, they cut through the secondary coil. Field lines being cut by the wire in the coils induces a PD, remember that stands for potential difference, voltage, in the secondary coil, which causes current to flow. So them growing out there creates a current flowing in this one. It's very clever, isn't it? So this PD will continue to be produced until the current in the primary coil reaches its steady value. When the current in the primary is turned off, so this is still talking as if this is a DC supply. I think I've talked about AC already. we'll get there. The magnetic field lines, where am I? When the current in the primary is turned off, the magnetic field dies away. The field lines will again cut through the secondary, again inducing a PD in the secondary. So turn it on, they grow out, cut across, turn it off, they shrink back and cut across again. So remember that a PD will only be induced in the secondary coil when current is increasing or decreasing in the primary coil. Once you have a stationary, like I don't mean stationary as in stand still, a steady value of current, then your magnetic field lines are just going to stay constant. They're no longer cutting across, they're not inducing a current in the secondary coil. So the induced PD can be increased by having a soft iron core or by using a complete iron ring as shown in that wee diagram. In real life, I was getting a wee bit ahead of myself. Instead of sitting and turning on and off a switch, an alternating current is used. So that means the current here in your primary is just constantly changing direction, which means that your magnetic field lines constantly are doing that. So constantly cutting across this and constantly, how many times can I say constantly? Constantly creating a current in here, and that'll be an alternating current as well because the magnetic field lines are constantly growing, shrinking, growing, shrinking. Okay, so this induces an alternating PD and a current is induced in the secondary coil. So over onto 241 then, what are transformers used for? So I think I mentioned this ever so briefly earlier, but it changes the value of an alternating voltage to either higher or lower depending whether it's step up or step down. So if the primary coil has more turns than the secondary, the voltage is going to be decreased in that secondary, so it's called a step down transformer. If the primary is less turns than the secondary, then the voltage is going to be increased, and that's a step up transformer. Has to be alternating current. Now, in order to work out how much the voltage will be stepped up or stepped down, you need to know the number of turns on the primary and secondary coils. We've got a good wee equation to write in here. Let's do it. So the number of turns in the coils are directly related to the voltage. So the number of turns in the secondary divided by the number of turns in the primary is equal to the voltage of the secondary divided by the voltage of the primary. So it's just like it's basically ratios. Okay, you could actually solve some of these problems just using your mathematical knowledge of ratios, but this is the equation that you use. Now this looks horrendous. We simplify it a little bit. Okay, so number of turns in secondary, we write that as NS divided by number of turns in the primary, NP, equals voltage secondary divided by voltage primary. Now, the lovely little thing about this equation is that you actually don't need to remember it properly. You do need to remember it, but you don't need to remember it properly. I could have written this, like I could have flipped this upside down and written it and it would still work. As long as, you see the way the secondary ones are both on the top and the primary are both on the bottom, as long as they're both on the same thing. So either both secondary on the top or both secondary on the bottom. Okay, and what I tend to do is write this as I need it for the question. So say my question was working out the primary voltage, I would probably write this, let me do it in pencil. Here we go. So if a question was asking me to calculate the primary voltage and it gave me all the other ones, I'd probably do VP over VS equals NP over NS. Do you see how they're the same mathematically? Like I've just flipped upside down and reversed it. So that is why I like this wee equation. It's a good wee one. It's a good wee one. Now over on to 242. I'm actually going to ignore this little tiny bit. It's such a small thing, but I'm going to ignore it for now because I want us to practice using that other equation. So I'm going to do 1A here, just like a wee example for you. Okay, so for each of these, calculate the output voltage. So output voltage is VS. This is our VP, our primary voltage. This is our primary number of turns, so that's NP. And then this is our number of turns in our secondary, so NS. So if I'm looking to get the output voltage, VS, I'm going to do VS over VP equals NS over NP. I've written far too big for the space that's available here. Right, anyway, I'm going to fill in my numbers, so I'll work across the way. So VS over VP is 2, is equal to NS, which is 80, over NP, which is 20. So that gets me 8 volts. Had a wee panic over my mental maths there, I had to check it. Okay, so hopefully you were able to follow how I was doing that. Do the same then for parts B, C and D. I'll have a wee look and see what other ones of these I want you to do then. Okay, I just want you to do to the end of page 243 today, and then we'll do the rest of them next day after we've done that wee power bit, okay? My advice here is to make a little list. So secondary turns in a 3-volt lamp is to be run from this power supply when there are that many turns on the primary. So make your wee list of, let me see, the secondary voltage is 3, that's this one. This here is the input voltage, so the primary voltage is 24 and the primary number of turns are 480. Okay. Right, that's it. I'm not going to give you any more hints for the rest of them. That is that. Give me a wee shout if you need any help. Okay.